Okay, let's start. Good morning. So this is Math 3210, fourth section, Foundations of Analysis 1. Basically, this class is single variable calculus, but with proofs. Right? That's the point of this course. My name is Alp. I'm a postdoc at the math department, my final semester here. And this is my email. And so today we're going to go over the syllabus, and if time permits, we're going to start talking about some math. Before I continue, I wanted to sort of gauge your sentiments. How do you feel about this class? You know, the room itself. You like it?
Oh, the room. Excited for the class. The room. It works. Yeah. Leaves something to be desired.
If you're kind of like me, this stuff just like is kind of overwhelming to me. But I'll see if we can change the room to a more classical room with no toys. But we'll see. It's likely that we're stuck with this room, and in that case, we're just going to do our best. Okay. So syllabus. So this is already on Canvas. I'm not going to distribute the physical copies. First things first, you're going to see sort of red font every once in a while. Whenever you see something red, that's a link that you can click on. I'm not going to go over the syllabus verbatim. Just going to mention some things. Well, the topic of the course is single variable calculus with proofs, but this course is also serving as, the transition into abstract math, and part of it is, being able to write proofs and argue rigorously about things, and part of it is mathematical maturity, whatever that means. Maybe I should ask you, what is mathematical maturity? Maybe you've heard this phrase. What could it be? I'm not going to be this nice going forward, so yeah.
Maybe being comfortable with proofs is part of it?
In a sense, yes, that is certainly a big part. As far as I'm concerned, me being sort of like a professional mathematician, compared to how I was back when I was an undergrad, the main thing I think that is different now is part of it is, of course, I'm relatively more experienced, but part of it too is, even if I encounter something that I'm not quite familiar with, I get to keep my poker face, okay? Somehow, for me, mathematical maturity is not sort of freaking out just because you don't understand something. And so this class is going to be really testing you in that regard. Given that you're taking this class, presumably all of you are pretty good at math, but the style is going to be somewhat different in this class. Perhaps some of you are going to, for the first time, encounter problems. Yeah, you can just come in.
The door's locked.
Oh my God. Okay, there's that problem too. Somehow, don't close it. Do I need to do this? Okay. Okay. What was I saying? Yeah, some of you are going to encounter problems for the first time, perhaps, in your lives that you can't immediately solve. It's going to take a while. And I'm going to do my best to come up with problems in problem sets that's going to take you at least multiple times, maybe a couple times to work through. Okay? So that's that. Expectations. Attend all lectures, okay? That's an important thing. I should mention I'm going to be recording the lectures, and I'm going to be uploading annotated recordings once per week on YouTube, and you're going to have access to watching these and so on. On the other hand, I'm going to be taking attendance at random days. So just because I'm recording doesn't mean that you don't get to come to class. I'm expecting you to come to class because part of it is, experiencing this phenomenon of getting confused and seeing other people also getting confused with you, so that, you build some solidarity and stuff. There's something really, how to say, unreplaceable about coming to class as far as I'm concerned. What else? 11 problem sets, 2 in-class midterms, and 1 final. And the style would be this. Every week there's going to be a boss fight, okay? And there's not going to be anything else. There's going to be either a problem set or a midterm, okay? And it's going to be always on a Friday. And so there's going to be the cyclical nature. Okay. There's a bunch of learning objectives, all that stuff. Let me write down the grading scheme. And so attendance, 5%, problem sets, 30%, midterm 1, midterm 2, they are both 20%, and then the final is the remainder, which I think is 25. Okay. And the grading, letter grades start at A, which is 90%, and then drops by 5% for each letter. Okay. Main textbook is the standard issue 1 by Joe Taylor. He was faculty here a while ago. He's now passed. It's been a while. I didn't know him personally, but I had read some of his papers a while ago. There's a bunch of other things you can have a look at. One thing I should say, even though we have a specified official textbook for the course, I'm not going to be following this textbook verbatim, as you might have gotten accustomed to from other classes, from lower level classes. And in fact, I'm going to change the orders a little bit, drop some of the topics, add some new topics. I've taught this class before, and after sort of deliberating as to what works and what doesn't work, I sort of made some changes, which hopefully will be nice. In particular, for instance, for integral calculus, we're going to be using a chapter from another book written on the syllabus, and it's already uploaded on Canvas. And for the infinite series or analytic functions business, we're going to be using yet another reference. That's, again, available on Canvas. There's more things. Lectures by Terence Tao, lectures by someone that I wrote there, Ali Ugar, and he was my professor. He was a professor I took this class from. It's not exactly the same class, but I think it will be useful. Another thing, of course, is that you have access to all the materials from the last time I taught this class, including lectures and exams, problem sets, solutions, all that stuff. Okay, these are all listed on the syllabus. And I've written down a tentative schedule. I'm going to try to stick to this schedule as much as possible, but things happen. I am a very improvisational sort of instructor, and so I like modulating the class, the tempo, the detail, the level of detail, and so on. So we'll, in a sense, sort of come up with what we're discussing throughout together. Like I said, I'm going to be recording lectures. It's unlikely that you're going to be in the camera because I'm just recording myself. But if that happens, privacy is an important thing for me. I'm going to make sure before uploading that you're perfectly anonymized and everything. Okay. problem sets, one problem set per week, and so on. Math Center, that's an important thing. I think there's like specialized tutors there, or people who are specifically for this course. And some of the students who have taken this class from me last semester or the year before are going to be working there, I think. So it might be good to look out for those people. Accessibility, the usual stuff. Inclusivity, usual stuff. I'm saying usual stuff, but you see, in previous years, I always read all these statements out loud. But I thought, I'll let you read the stuff on your own this time. And maybe tomorrow we can discuss if you have any questions. Okay. One thing I should mention, AI stuff obviously is an important matter in this day and age. I'm generally OK with you using AI insofar as it is responsible, whatever that would mean. Of course, part of the course is going to be figuring out what that reasonable use of AI is. Now, I was born in '92, and so when I was younger, at some point, Wikipedia came around, and all my friends started using Wikipedia as the only source, and so on. And then humanity realized, oh, maybe this is not the way you should be using. Maybe it's like the starting point. OK, that's good, but all that stuff. So the way I imagine this, maybe I'm sort of talking about all this stuff from the sort of old vanguard point of view, but nevertheless, as far as I'm concerned, LLMs should not be the final destination in whatever you're doing, but it's a very good, I think, starting point. Case in point, and there's a link to this as well, U of U recently made a contract with OpenAI, and now you have access to the latest models of ChatGPT, whatever, through the university. So this is this ChatGPT Enterprise EDU, and it's pretty good. And I would suggest that you at least have a look. This is not to say, of course, in order to succeed in this class, you have to be using LLMs. But given that this is a reality of us regular people now, I think it would be good for you to experiment a little bit. OK. That's that. Any questions about these things? Fairly straightforward. Maybe I should ask you, how many of you have some experience with proofs? Okay. Is that from discrete math type of thing? OK. That's kind of a double-edged sword, because the proofs that you do in discrete math, they have a different flavor, to say the least. In discrete math, of course, I'm exaggerating, but the point is, you have a bunch of things, you count them. There's like a formula coming from combinatorics. You do this, that, whatever, and then you get the number. In calculus, proofs are more fuzzy. It's mostly about approximations, and the style is rather different. And so don't be surprised if it kind of feels weird, OK? Those of you who are familiar with proofs. Good. Any other questions, comments? OK. So we start from the beginning. Let me see. Good. Oh, another thing, of course. It's a major problem as far as I'm concerned that this class starts at 8:30. Not necessarily for me, but I can relate. Back when I was taking courses, I didn't want to get up at whatever time, or at an early time. And given that this course is meeting 4 times a week, that essentially means that either you're going to be sleep deprived rather frequently, which is not good, or you're going to be missing classes, which is again not good because I'm taking attendance. Okay. So I would highly suggest that insofar as you are capable of doing this, that your plan, your schedule allows this, try to make an effort to go to bed early. This is sort of like an obvious point, but it's good to state it, I think. So I will be here, of course, every day, but I hope you'll be here too and not sleeping. Okay. So that's that. We start from the beginning, and the beginning is, even though they don't really discuss these things in the textbook, we're going to start from the logic. Logical symbols and operations. So the first part of the course, let me mention this. Week 1 is titled functions. Then the next week is reals. The next week is sequences. And then we go to continuity, and then we're off to the races. But basically, the first 3 weeks are pretty much like the foundations, and especially the first 2 weeks. And so I'm going to be rather fast about these kind of things. I'm not going to worry too much about, the formalities of things. Despite the fact that this course is a proof-based course, okay? Because somehow it's also true that you can also do too much and focus too much on the foundations, which would paradoxically take us away from calculus proper. Okay. Logical symbols and operations. These are not technically necessary to state, but I'm going to be using them quite often in this course, and it's part of the standard vernacular, let's say, of the modern mathematician. And so we might as well get accustomed to these. So it's like beans and stuff on the floor. Okay, so you have this upside down A. That stands for all. For now, let's just take these as symbols. So technically what are called logical quantifiers. This is the universal quantifier. Then you have this backwards E. That's an element of. Sorry, there exists. Sorry. There's another E for that. And then if you have backwards E with a bang, that means there exists a unique. So these are the symbols. What we're going to do is we're going to sort of use them to list a bunch of variables in our formal statements. Technically, instead of using these symbols, you could use these phrases as well. But as far as I'm concerned, being able to write for all fast like this is a good investment. When it comes to operations, we have the standard and, or, XOR, what else? Not, implies. Not, implies. Perhaps the most bizarre looking one is this XOR. How many of you have seen this before? Yeah, they use it in computer science typically. So OR is, for instance, I have, let's say, I have a Facebook account and an Instagram, or an Instagram. Or you look at the people who have either a Facebook account or an Instagram account. That's OR. XOR is this exclusive OR. If you want to say the people who have either a Facebook account or an Instagram account, but not both. Okay, maybe we can symbolize these using Venn diagrams, like so. Okay, and corresponds to this intersection, or corresponds to the union, of course. XOR corresponds to this, but not this. You get rid of the middle parts. Not, it's the outside in a sense. Right, these are sort of the Venn diagram visualizations. Let me first ask, is this kind of clear what I mean when I draw these? Don't worry, as time goes by, I'm going to speed up. Today we're sort of getting accustomed to these kind of things. I also didn't sleep that much last night. I wasn't able to sleep on time, so I'm taking it easy. But then, how do I get to represent the notion of implies, or the symbolic or logical operation of implies using sets? Any guesses?
Asking for like the symbol, like the little arrow thing?
No, like a sort of caricature, something like this.
The statement on the right is a subset of the statements on the left, but the statement on the left.
Right, so then I can, instead of sort of drawing it like this, I could do something like this. And you might as well say logical operations correspond to set operations, and that is indeed true. But that's sort of like a foundations axiom, which basically says well-defined properties in math can always be turned into sets. A property P, you can say, it's a logical statement, or you can say set of x's that satisfies property P. So there's this correspondence, and we're going to keep using these. And that's all I need for now, really. That's all we need when it comes to logic. I'm going to keep using these notions throughout, and I'm going to keep reminding you what these mean and so on. But as far as I'm concerned, at least for this class, taking these as naive things, intuitive things, is going to be sufficient for us. There's a deep study of this, but that would be like logic or set theory, whatever. We're not going to go there that much. Any questions about this? Yes?
Is the implies one like the big circle implies the small circle? Or what is it? What does the symbol mean?
Yeah. Maybe I should ask you. Can you explain?
When you think about like the set of all statements, the statement on the left is probably a subset of that, and then the statement on the right is an even smaller subset.
Sure, but there's no statement on the left here, and I could have drawn the arrow the other way around too. What do you mean by left?
I think it's just saying if it's in the smaller circle, that means it's also in the bigger circle.
Yes, essentially, right? So it's the other way around. That's sort of like bizarre a little bit. I get why you're sort of asking this question. But it is like that. It's like, because in a sense, imagine, how to say. So let's say the smaller disk, let's say, instead of the circle, because in these Venn diagrams, you're supposed to be sort of thinking of the meat of the thing. The smaller disk, let's say, represents the students at the University of Utah taking this course. The larger one is all students enrolled in some course in the University of Utah. Okay? So the smaller one is in the larger one. Okay? In other words, if you're taking 30 to 10, officially, that means that you have to be a student. Not vice versa, but okay. Does this kind of make sense?
Yeah.
Okay. I like the enthusiasm. As time goes by, we're going to get faster and faster, but it's going to be your job to keep asking questions, okay? I know it's hard because, it's early in the morning and everything, but such is life. And you enrolled in this course. Granted, of course, maybe you have other responsibilities and so on. I'm not disillusioned about that. Question? Oh. Okay. And by the way, if you have questions, you don't need to raise your hand and stuff. You can just shoot. Cool. That's that. Set theory. Now, set theory is one of these branches, perhaps, of math for some, or logic for some, or it's its own thing for some other people. For us, it's going to be this. It's this statement, it's this paradigm that everything in math, as far as we're concerned, is going to be basically underneath the hood. It's going to be a set. So set theory as foundations. Everything in math is eventually, when you sort of chase the definitions and so on, is a set. Okay. How many of you are familiar with this idea? Some of you, yeah, kind of, sort of, yeah. Why do you even say this? Because there are alternative choices for foundations. One of them is, for instance, type theory. Everything's a type, they say. One of them is category theory. Everything's a category, they say. Even though these are not incompatible, these are not incompatible from each other. They are all compatible in a sense, but this is sort of the most user-friendly, and this is also what the textbook uses, so we're just going to stick to this. And so when I say everything in math, I mean objects, okay? Functions, well, mainly functions, but numbers and stuff like that too, ultimately, if you try to sort of formalize it, you end up formalizing them as sets. This is kind of bizarre. That's why we're not going to go into that. But that's how you do it in a sense, these numbers and stuff. Okay, what is a set? This is so in the textbook they say a set is a collection of things, but then what is a collection, okay? And technically a collection is something more specific, so instead of using the word collection, I'm going to use the word, which is non-mathematical as far as I'm concerned, aggregate. A set is just an aggregate of things. Of stuff. What is allowed, what is not allowed? Let's not get into the philosophy of this. You're going to see it's like pretty much everything that we're going to worry. Question?
I was just saying the set of all sets contains itself.
Yeah, don't go there. Yeah, you can sort of. The point here is that, like your colleague is suggesting, if you force these foundations, you start breaking things and you get into inception, whatever, okay? Don't do that. We're not going to need that. Calculus is pretty nice. Everything is, it's going to be sort of, it's going to be scary in its own way, okay? So we don't need to introduce those kind of things. But you're right, yes. There's a bunch of games. So that's that. What are sort of typical examples of sets that we're going to need? Well, they're going to be basically sets of numbers. What is a number? Again, let's not go into that. A number is what you believe it is. But of course, there are different sets of numbers. And this is going to be an important thing for us. Let me just check. It's going to take a while for me to get accustomed to when we stop. Okay. So examples. And so for instance, natural numbers, naturals. Integers. Rational numbers, rationals. What else? Irrationals, right? And reals. There are many more, of course, but let's just first focus on these. And in fact, let me just drop irrationals, because it's good to think about this sort of hierarchy. Reals. Now, these are just words. These specific sets of numbers have specific notation, okay, that is common to use. For naturals, you use n. But instead of just writing n, typically what people do is they put a dash here. Technically, this is what is called blackboard bold. I think what people used to do is, even though this is a whiteboard, back in the day, they would just take two pieces of chalk or pieces of marker, two markers, and maybe draw something like this. I don't quite know. But this is sort of what we do and what we say. Blackboard bold. That's the name of the font. Anyway, not that important, of course, that we do this, but I'm just saying a bunch of things so that if you try to read things out on your own, on Wikipedia, whatever, you're not sort of confused. Integers doesn't start with E or I typically. It starts with Z, and that's the first letter of the German word for integers. Rationals is denoted by Q, and reals is denoted by R. Okay, these are the main sets of numbers that we're going to be interested in. Okay. How many of you have seen notation like this before? Okay. Pretty much all of you. Good. How do I get more explicit about what these are? Well, there's a bunch of different ways of doing this. Writing things out explicitly. Sets explicitly. First method is basically sort of listing them down. By the way, instead of writing n, I'm never going to use n. I'm going to use this notation. Z with a subscript greater than or equal to 1. Why? Because, I want to avoid this question of whether or not 0 is included or not, all that stuff. Believe you me, it's going to be an issue every once in a while. So I never use this, okay? I never worry about this 0, whatever. If I need to include 0, I'm going to write z with a subscript greater than or equal to 0. Anyway, so how we can write this is like so. You use what is called these curly braces, okay? And you just list them down. And so technically, this is an infinite set. I cannot just list all of them down. So what you do is you write a bunch of them, and then you put ellipses. Now, from a certain point of view, one could say, oh, this is not the set of natural numbers. This is just a set of 4 elements, 1, 2, 3, and ellipses. You can do this, but let's not do this, okay? Let's not go there. There are certain levels of formalism one could engage, whatever mathematical statement you have. And especially when it comes to these sort of pedantic matters, we're not going to worry too much about these. You're going to see throughout this course that we're going to have so much more other things to worry about anyway. And, there are some people who do worry about these kind of things. I'm saying all this because some of you might be naturally inclined to think about these kind of matters. So I don't want to be gaslighting you that these are not problems, these are not things that people don't worry about. It's just that in this course, we're not going to worry about it that much. One thing I should say is that these, let me try to, it's kind of hard to draw. Okay. One thing here is that when you're using this list notation for sets, the order in which you write things down doesn't matter. Okay? So instead of writing it 1, 2, 3, whatever, I could have written 1, 3, 2, 4, 5, 7, whatever. I almost did 6, 7 here. Okay. Trying to come to terms with the fact that I'm getting older, you see. One of those cool kids now. Anyway, integers, well, you have the negatives as well. I can do this. Let's write it like so. 1 plus minus 2, plus minus 3, whatever. Now with rationals, let me introduce yet another way of writing sets down. This is what is called the set builder notation that I'm going to use. So you open braces and close braces, and you put a bar in between. Okay? This format is what is called the set builder notation. Sometimes you might see sort of a column here. I like to use a bar. So this is set builder notation. There are two spots here. Okay. Here you put the format of the general elements in this set that you're trying to build. General form. Form, am I right? And on the right, you put the condition that you can possibly verify to figure out whether or not this, whatever thing that you're looking into, should be included in this set. Condition. Okay. And so if this is the case, I might write it like so. General form of a rational number should be the ratio of two integers, p over q. Okay. And what is the condition? P and q are integers, but of course, we don't allow q to be 0. So I might write it like so. Okay. And here is yet another symbol that we're going to keep using. This is the element of symbol. I'm saying here p and q are elements of integers. Okay. So let me record that as well. So. Okay. So typically, you write it like so, okay? And so you put something to the left and something to the right. The thing you put to the left is the point in the Venn diagram, okay? The thing on the right is the set. Now, typically this is the order in which you write things down, but you might also see it the other way around. Okay? Doesn't matter. Or maybe you might see something like this in sort of day-to-day discussion. This always means whatever is on this side is an element of the thing on this side. Okay? That's an important symbol. And again, technically, you don't need to use a symbol, but I suggest to you that instead of writing this many times, using this symbol is going to be rather useful. Okay? So I'm introducing all this notation so that when you're trying to do math, you're not going to need to keep a lot of things in your mind, and you're going to be able to sort of record what you're thinking about rather fast. That's the main point. And I think one of your colleagues mentioned this other symbol as well that is used in set theory. It's this symbol. It's similar to the element of, takes two things. You put something on the left, something on the right. But instead of having the thing on the left being an element, this means the thing on the left is a subset of the thing on the right. Okay. For a while, I'm going to keep reminding you. I'm going to keep using these symbols, but I'm going to remind you what these mean. And at some point, what might happen is, while you're seeing these like logical symbols and stuff like that, and at some point, it becomes like gibberish. Okay, you sort of cannot sort of figure it out, what it actually means. If that happens to you, what I would suggest, or what I used to do in those kind of situations, would be, well, I would write down the logical statement in simple English. Okay, just decode everything, expand everything out, and eventually you're going to get used to it. Okay. Any comments or questions about any of this so far? Now, one thing I should say is this is somewhat different, this notation, than what is used in the textbook. In the textbook, I believe, instead of writing like this, they just use this, okay? Meaning they don't put this line underneath. I'm never going to use this symbol because this is somewhat ambiguous if you consider other literature. The reason why is that I'm imagining this subset of symbol similar to less than or equal to symbol for numbers. Okay, we're going to talk about the analogy, the nature of this analogy later. So this is what is really called a relation, really. We're going to say that this thing itself, we're going to see, is a set. This itself, so is this and stuff. And we're going to call it a specific type of set. It's going to be a relation. But the point is, I want to think of this similar to less than or equal to. And just like this kind of means strict inequality, and this is not the strict inequality. Just because there is ambiguity, I'm going to always use this. And if I mean strict inequality, I'm going to explicitly draw a dash through this line. So proper subset. Okay. Now, what is the difference between subset of and proper subset of? Well, this means the thing on the left is not allowed to be exactly the same thing as the thing on the right. Just like with numbers, you can say 5 is less than or equal to 5. That's a valid statement. But 4 is strictly less than 5, for instance. There's these two differences, these two notions. And likewise, I want to have these two symbols representing these two. Okay? Any questions or comments about this? How do you write down the reals? well, this is really the part that I'm going to skip. How do you formally write down the reals? That sort of is involved, rather. So we're just going to take reals as they are. What does this mean? This means it's a certain set that contains all rational numbers and then some. And this is sort of like the optimal. We're going to call this the completion, analytic completion of the rationals. We're going to get there later. But this, for us, essentially going to be where intuition comes in. And when I try to represent the set of real numbers, I'm just going to draw a line. Okay. Again, technically, I'm assuming things here. When you're talking about sets, there is no shape to it. So you don't get to make this identification. But for our purposes, it's going to be perfectly OK to do this. OK. And so what we can say is, well, naturals is a subset of the integers. We're also going to say integers is a subset of rationals because, n is n over 1. So that's allowed. And rationals is a subset of reals. Okay. There's, of course, more sets you can keep going. And presumably, if you've done anything algebraic, let's say linear algebra, whatever, you've also heard about like complex numbers and used them. But we're not going to get there. Technically, this course is real analysis, or calculus for real spaces. There is analysis using complex numbers as well, but that's a different course. That's a more advanced, in a sense, course. Okay. The flavor, surprisingly, is rather different. Okay. Any comments or questions about any of this?
Would the reals be a subset of the complex?
Exactly. Yes. Very good. Okay. Okay, we covered plenty of things, actually. Okay, so I think it's a good place to stop for today. I'll stop a couple minutes early. I'll see you tomorrow. And like I said, I'm going to try to change the room, but nothing to promise, unfortunately. Okay, let's start. Good morning. So I contacted Professor Zhu, who is handling course assignments and so on. And it seems there is some hope for a change of a room. He told me that this class really is sort of engineered toward math education courses. And that's why I have all these toys around. And clearly, we're not going to be dealing with that in this course. So we'll see. So I asked you to perhaps have a look at the syllabus on your own yesterday. I wanted to ask if you guys have any questions or comments about how things are going to work. I'm going to keep asking this throughout this week because this week is still the week of, window shopping. You're still probably thinking about whether or not to take this course and stuff. Maybe some of you are, at the very least. But nevertheless. Okay. Yes?
Sorry, it says for like the submission details for the problem sets, it mentions like Google Forms and Gradescope.
Yes.
Could you like clarify that a bit? Because like I've never like done that for.
Yeah, that's something, that's a good point actually. That's something that I've been experimenting with for quite a while now actually. So submitting a problem set is going to be a two-step process, okay? One is your actual math work, and the second is you telling me about it, okay? So in this Google form, I'm going to ask you things like, how long did this problem set take you? Which problems were harder? Which sources did you use? This is also where you would sort of disclose, oh, I used ChatGPT, whatever, as well. Okay, so, and, or maybe it's like, oh, this problem set was too long. This specific problem was like too cumbersome. These kind of things. So week after week, I'm going to keep asking you to give me feedback about where you are. And depending on how we're all feeling, I'm going to sort of try to modulate the course. That's sort of the style that I've been developing recently. It's like, it's sort of like more compatible with my psychological makeup as well. Like I like somewhat of an improvisational approach, and I like to sort of modulate the course depending on the types of requirements I see students have. Does that kind of make sense? Yeah. We have obviously certain things we need to cover, but there's a lot of things that there's a lot of things that are negotiable in this class in terms of topics and stuff like that. So we'll see how things go. But yeah, that's the main thing. Yeah. I've been sort of doing this ever since I started here, actually. I've been doing this for 3 years now, the sort of Google form and a problem set solution, or solution submission type of thing. And the first few weeks, some of the students end up having some issues with the procedure, so to speak. But eventually, pretty much everyone sort of figures it out. So, okay. I know it kind of sounds weird a little bit, but once you get the hang of it, it's gonna, I hope, make sense a little bit. Okay. Any other questions or comments? Okay, so I want to start with, so we have a couple things that we still need to discuss from these foundations, logic and set theory and stuff like that. And I thought it would be a nice idea, this is something that I like talking about, a certain, in fact, experiment from psychology. Some people in psychology, they like to experiment with people's understanding of how logic works. Okay? They don't tell them, oh, this is how you reason about things. And indeed, there's some amount of, how to say, negotiation there to be had also. It's not super clear what the rules of logic should be in general. But in math, obviously, we use a specific type of logic that goes back to probably like Aristotle, if not even before that. So I'm going to give you a task. I'm going to describe a task, and we'll see if you guys can come up with the solution. So this is the idea, okay? I have a deck of cards. On one side, each of these cards have a number. It's an integer. The other side it's the back side. It's either, let's say, blue or red. Okay? That's my deck. In front of you, you see a table. That's somehow the table. And I deal 4 cards to you. Okay? First card, you see 3. On the second card, you see 8. The next card, you see a blue side. Okay. So that means on the other side, there's a number, right? And the last one is a red card. Okay, so far? So you get to flip if you want. I'm going to ask you something in a second. I make the following claim. If on one side of a card, if on one side of a card you see an even number, then the other side should be blue. I'm not saying this is true or false. Okay, I'm just claiming something. In other words, even implies blue. Okay, that's my claim. Could be true, could be false. The task is, well, what do you need to do in terms of flipping some or all of these cards to verify or deny with complete accuracy this claim?
We're already told that colors are strictly blue or red, right?
Yeah. There's no gimmick here. I'm not sort of like trying to trick you.
I would say flip the 8 and the red.
So you're saying flip the 8 and the red. Anyone else? Any other guesses? So one strategy is now let me just reiterate, what does your colleague suggest? To verify or deny this claim, all I need to do, he says, is that I would need to focus on these two cards and just flip this to look at the other side, and I'll flip this to look at the other side. Your colleague really suggests that I don't really care about these two. Does this make sense? Oh, go ahead.
Oh, I was gonna make another suggestion.
Yeah.
I would flip the 3, 8, and the blue.
So flip. Okay. So your colleague suggests that, oh, you know, just looking at these two, you might be able to say something, but not with 100% accuracy. Okay, we're not doing anything, you know, random here. First, yeah.
I would just flip the 8. Because all it's asking about is even numbers.
Then,
Just flip the red.
okay. Okay. Any other suggestions? As time goes by, we're going to pick up the pace, but you know, this is the first week and stuff like that. So, and I want to be. Yeah, you could do that, but the point is to be, you know, frugal. You don't want to do too many. So you're saying perhaps, are you suggesting that I should be actually looking at every single one? Yeah. Okay. Now, perhaps surprisingly, the first answer is the right one. Okay. This might be bizarre to you, okay? No judgments, but the type of logic we're going to use really matches with the first answer. There are many logics, but we're going to stick to the classical one, and that is the one that is used in the textbook as well. And here's why. I want to verify if even, then blue. So I don't need to flip 3. It's odd. I don't care what's on the other side. The other side of this card could be blue. It doesn't say all cards on the other side are blue. Or, you know, maybe 3. The specific odd number 3 is blue. All other ones are the other way around, whatever. So I don't need to care about this, this first card. The second card, you would need to flip because 8 is an even number. It is divisible by 4, right? So what is an even number? Well, it should be an integer multiple of 2. If it's not even, it's odd. That's the definition of an even number. So you would need to flip this guy. How about this? This is perhaps slightly tricky. This is not saying that the only way, so this claim is not about, so the claim is not making any comments about where the blues are ultimately. the totality of them. It might happen that there are some of the cards that are not even, that are again blue. This statement doesn't say anything about that. So again, I don't need to care about this. But surprisingly, you see, if I don't flip this, maybe on the other side I have a 1. Okay? If I had a 1 on the other side, without flipping, I wouldn't be able to know this. But then this claim would not be true. So to verify this claim, I would need to look at the other side of this card. This is very bizarre. I understand. So I'll let you think a little bit about this. But later this week, we're going to start talking about different methods of proof. There are certain well-established and accepted methods of proof associated to this logic system. And we're going to say, for instance, looking at the other side of this 8 really corresponds to what we're going to call direct proof. Okay? So this is going to be direct proof. I'll mention what that is, and I'll give an example later. So that's a direct proof. On the other hand, this one, needing to flip the red card, so in a sense you're going backwards there, it is what is called proof by contrapositive. It's not contradiction, that's a different thing. We're going to talk about that as well, but this is what is called a proof by contrapositive. Okay. Comments, questions? Okay. So, and don't worry if you didn't get this quite right. In math, we like to pretend that things are obvious or things are intuitive. But in reality, as far as I'm concerned, they aren't really. Math has its own sort of logic and stuff like that. And so part of this course really is getting accustomed to these ideas. Let me say a couple more words in case you're interested. Part of this psychology experiment is also that, well, they come up with like different versions of this that has more social implications, let's say. So for instance, there's like a problem about checking people's IDs at a bar to figure out if it is legal for them to drink an alcoholic beverage, for instance. In that case, for instance, it turns out that a lot of people, even though they might fail at this, they figure out that the other one correctly. So somehow, the point of this psychology experiment, part of it, is that if there are certain social rules, if there's a context, people are much more successful at figuring these things out. But of course, this course is not a sociology course or a psychology course. This course is about abstract math. And so that's going to be a real challenge. Okay? Any comments or questions about this? Okay? So we have a couple of things that we need to still define. Set operations, these are going to be very similar to the logical operations that we discussed yesterday. And whenever I define something, I'm going to underline the phrase that I am defining in that sentence. Okay? Sometimes I might say, blah, blah is by definition to emphasize that I am defining that thing. But here I didn't do that. And so here's the definition. It's a bunch of operations that you apply to sets. Let X be a set, and A, B be subsets of X. Let's remember from yesterday, this is a notation for this is an abbreviation if you want, for the statement that A is a subset of X and B is a subset of X. Instead of writing that out loud or explicitly, I just write this. Okay? Intersection. Intersection of A and B is now a new subset of X. And you use this symbol, A, and then this cup, or rather cap is the term for it, I guess. B. And again here, remember this is what is called the set builder notation. I have open braces, close braces. I have this bar. And what was the rule? To the left, I write the form of a general element. Okay? So I'm saying X and X, that's the general form. And on the right, I'm going to write down the condition that I look into to figure out whether or not an X should be included or not. That's the rule for the set builder notation. And just to reiterate this connection between logic and sets, let me write this as well. So X and X such that X is an A and the way we discussed yesterday, X is in B. So the intersection of two sets is the collection of all those points, all those elements in your larger set that are contained in both. Fairly straightforward. This is, how many of you have seen something like this before? Okay, pretty much all of you. And again, let's remind ourselves, what is this symbol? As opposed to this, this means this is an element of this. Again, instead of writing it like this, I could have written X is in X explicitly, or X is an element in X, such that blah, blah, blah. And in fact, let's do this as well. You could have defined this intersection purely using purely standard English. You could say the intersection of A and B is the collection of all those points, or maybe I should say elements, of all those elements in X that belong to both A and B. Okay. Now, if you don't like this more compressed notation, this is perfectly valid as well. Remember yesterday I told you over time what might happen is, well, this logic stuff allows you to compress a lot of information. And at some point, you might start getting confused about things. If that happens, I told you, well, open everything up. Okay? Is this okay? So this statement is the same thing as writing this. Perhaps one issue, of course, in using standard English is, well, you start using sort of looser language eventually. Part of math and part of this course is, well, as opposed to the single variable calculus class that you took before, we're really interested in being very precise with our language. And so, for instance, from an outsider's point of view, I immediately question this. What does it mean for something to belong in a set? Of course, it's clear what it means here, but eventually, once you start looking into more and more complicated statements, words start to lose their meaning in a sense, as far as I'm concerned. It's still good, of course, and it's still important to be able to interact with the math, both at the formal level and perhaps also at the more day-to-day level. But underneath, really, formalism, at least for the first couple of weeks in this course, is going to be the main point here. Any questions or comments about this? Okay. And so that's the intersection. The union, it's pretty much the same, but you flip it this way, right? So now this is a union, and it's the set of all those x's such that x is in either A or it is in B. Okay. Symmetric difference. It's this triangle symbol. This is not as common as these two, but it's still fairly straightforward. It's fairly common. Instead of or, if you were to use XOR, exclusive OR, you would get the symmetric difference. Relative complement. A takeaway, that's how I would read it, or you could say set minus. B is a set of all those points that are in A but not in B. And here's another symbol, and this is sort of the general schema. Whenever we have a symbol, if you put a dash through it, typically, that turns into not that. Okay? So instead of, so here, for instance, this means X is not in B. Okay. For a subset, I could have done the same thing. So D, not a subset of E, for instance. I could have written it like so. Okay. So maybe I should write that as well. Not a subset of E. And then finally, the absolute complement of a set. Typically, you don't say absolute, you just say complement. This is a common notation, A to the C. And you look at the relative complement of A in the larger set X, which then turns into this. So these are the basic operations. Any comments or questions about these? Okay. Let's move forward then. I want to define a certain class of subsets of the reals that we're going to use in this course quite a bit. And these are what are called intervals. How many of you have heard of the phrase or word interval before? Okay. Now, there are multiple sort of flavors of intervals. But it turns out that there's a definition, there's one definition that really covers all possible intervals you can imagine. Okay? And it goes like this. Definition. Let I be a subset of R of the reals. Okay. I is called an interval if it satisfies the following property. satisfies the following property. For any x and y in I, and for any t between 0 and 1, if I were to what is called linearly interpolate x and y, any of these linear interpolations I want to be still in I. Okay? So let's write it using these logical symbols for any xy in I, and for any t, let's write it like this, real number if t is between 0 and 1, then 1 minus t x plus t y is in I also. So this is going to be the general format of a logical statement. Okay? And I'm being somewhat pedantic here. Technically, you don't need to write it like this, but I thought it would be a good idea to see an example of a logical statement like so. Now, whenever you see something like this, okay, the first thing you should think of is this. Really, I want to have, in general logical statements, a bunch of things, variables like this, with quantifiers. Okay? And then I have a hypothesis, and then I say that implies this. And this statement in and of itself is the property that defines I, or that determines whether or not I is an interval. So surprisingly, this statement says something about I. In a sense, you could say this is the, so I is the only unbound variable here. Now, but what does this say? And this is where sort of the mixture between formalism and intuition comes into play. For instance, at this stage, I'm not going to question things like, oh, what does this addition mean and stuff like that. There's a version of this course where you also worry about this, but we're not going to worry about these kind of things. So what is happening here? Well, yesterday, we talked about how, R we're going to think of as pretty much like a line. So it's like this. Okay. And this I, the subset, is something that consists of a bunch of real numbers then. What does this statement say? It says this. If I have any 2 points, x and y, somehow, let's say, you're given that indeed these 2 points are in your set I. You're given this. Then I take another variable, t, that goes between 0 and 1. But the point of this expression here is, well, this goes from x to y as t goes from 0 to 1. This is what is called linear interpolation. Okay? Right? So because if t is 0, this goes away. This is just x. Then let's say 0.1, 0.2, whatever, all the way up to 1. When it's 1, when t is 1, then this is 0 and this is 1. Does this make sense? And so this is what is called linear interpolation, or lerp. in simple English then, what is an interval? An interval is any subset such that if you have 2 points in the set, you also have any other point in between. Okay, so in a sense, it's like connected. Does this make sense? Okay. There are a couple different types of intervals, and they ultimately all can be classified by determining the endpoints. If this were a different class, this would be a statement to prove. But for us, I think we can just take this essentially as definition. In other words, so let's write it like this. Thus, any interval is of the following form. Following. Is of one of the following forms. One of the following forms. For, let's write minus infinity less than or equal to lambda. Lambda is the Greek letter for L. I use that for the left endpoint. Then rho is the Greek letter for R. That's for the right endpoint. And infinity. And what does this mean? This means that I'm technically allowing minus infinity as well. Let's not worry about what that means, but we're going to talk about it perhaps just a little bit. We have lambda and rho with square brackets. Now, as opposed to these curly brackets that we were using for arbitrary sets, for intervals, we're going to use square brackets. What does this stand for? It's a set, right? It's an interval. And I can, again, determine or describe what it is using the set builder notation. This is the set of all those points in R, all those real numbers, such that lambda is less than or equal to x, and x itself is less than or equal to R. Meaning the endpoints are included. You might have heard the phrase closed interval. Okay, this is also something that we're going to use, closed interval. If both of the endpoints are included, well, you might at this point say, what if lambda is minus infinity? We're again going to call it a closed interval, okay? And technically here, surprisingly you see, I'm not saying that lambda has to be strictly less than rho. So in principle, I could write something like lambda to lambda, or let's say 0 to 0. This is, of course, just a fancier way of writing the set that contains only 0. So this is allowed, okay? For pretty much everything we're going to do, this is going to be something negligible, but we don't need to sort of worry about making lambda strictly less than rho. So that's one. The other kind is this. Now, probably, even those of you who have seen intervals, haven't seen this notation. So this is basically, again, square brackets, but the other way around. This is going to stand for pretty much the same thing, except that the inequalities are going to be strict. So this is what is called an open interval. Just to reiterate, okay, so this is strict inequality, and so is this. The more classical, or rather I should say, the more American or Anglo notation for this is just using standard parentheses. Okay, this is the same thing. Probably you're familiar with this notation. I'm not going to use this notation. Part of it is because this looks like a point in the plane, like an xy coordinate. I don't like this. So we're going to use this notation, and this really comes from the French school. Okay. You're going to get accustomed to this as time goes by. Now again, maybe I should mention this. Why not just stick to the basic notation? Well, I justify this again by referring to this mathematical maturity. It's a fact of life that math is used by many people. Same thing often is used by many people, but often they use different notation. They call the same thing different things, or they use the same word, but that refers to different things depending on the context. Just like, let's say, if you're reading a novel, whatever, you wouldn't expect the meaning of one word to be the same everywhere else, or one person sort of talking about the same thing in exactly the same language. So too in math, people have different notations that they use. And part of developing mathematical literacy, which is part of, as far as I'm concerned, mathematical maturity, is being able to decode different notation and somehow see the truth behind the notation. Okay? There are a couple more. So you can sort of come up with a mixed type. So for instance, you can do something like this. This is a half open, half closed interval. And so this would be the set of all those points that are, again, between lambda and rho. You include lambda, you don't include rho. Okay? And then you can do it the other way around as well, of course. Any comments or questions about these?
Just want to clarify the x that you're putting under those inequalities. That's just to explicitly note that it's not including rho or whatever.
Exactly. So this is not an x. This is a dash. So like I'm saying not. Yeah. You could also see something like this. Sometimes you would see this less than or equal to. This is like more archaic notation. And people would put this. You know how like this is equal and then this is not equal? It's pretty much the same idea. Yeah. So these are going to be the main subsets, and in fact sets that we're going to use. And what is the idea behind this notation? Even though it looks kind of bizarre, the idea is that you get to think of intervals, any one of these, as Lego pieces. Okay? So here's, for instance, a couple examples. So 0, 1, closed. So I could imagine this like so. Okay, that's 0. That's 1. And everything in between is included as well. And what is the significance of these dots? These are filled in circles. So you get to include the endpoints. But if I were to do, let's say, this, 0 included, 1 not. Okay? So here's 0, here's 1. Now I'm going to denote the side, the right endpoint with an empty circle. That's kind of the visualization I have. How do I get to think of these as Lego pieces? Because, for instance, there's union 1, 2. Something like this. So you see, I'm thinking of these as Lego pieces. These endpoints match. You put them together, gives you 0 to 2. Does this kind of make sense? Whereas if I had, let's say, taken the union of this guy with this, you see there is a middle point missing. 1 is missing from this set. And I cannot quite write it as an interval. And in fact, this union is not an interval. Okay? Right, so I could perhaps draw it like so. Okay? Yes?
On the 0 to 2 with the closed brackets, would we write it similar to the first one, like 0 to 1, where we just ignore the 1 point in the middle of the 0 to 2?
Yeah. So maybe ask again.
So if you were to draw the 0 to 2 on a number line, would it look similar to the 0 to 1? You're just skipping the 1 point in the middle, right?
Exactly. Okay. I think we have about 5 minutes. So let's try to engage with the statement I just made, really. I said this is not an interval, this union. You see, if you take 2 intervals, you can take the union of them. That's fine. But that union need not be an interval anymore. How could we perhaps engage with this idea? So claim. So in this course, this is what's going to happen typically. We're going to have a claim. Sometimes they're going to have like specific names, things like lemma, proposition, theorem, whatever. But they're all ultimately claims to be verified or denied. And there are a couple of different proof methods. Maybe I should ask you, how would you argue to deny or verify this claim?
You could assume that it is an interval, and then use the fact that if you pick 2 points around the 1 and then a certain t, that middle point 1 is not in the interval, so therefore it can't be an interval.
Exactly. So what your colleague is suggesting is yet another proof method that we're going to use, and that is called proof by contradiction. Okay? I'm going to describe it more carefully later this week, but let's write it like so. And the main idea of the proof by contradiction is this. You see a claim, you say, even though it is wrong, you think, or in this case it is correct, of course, you say it is an interval. And just assume this and see where certain considerations take you. Just to be a little bit more formal in our proof writing. So initially I'm going to be like rather strict as to how we're writing proofs, but eventually I'm going to stop writing things out explicitly. I'm going to start only referring to the full proof, okay? Suppose for a contradiction that the given set, let's call it S, interval is an interval. One could say, but then 0 and 2 are in S, but for, say, t equals 1/2, 1 minus t times 0 plus t times 2, which you're going to see is just 1, is not in S. You don't need to write it like this. I'm just like being extra pedantic right now. But that's a contradiction, because in order for S to be an interval, this linear interpolation has to be in S. You see? A contradiction. Contradiction. And when we end proofs, typically people put something there. If you're sort of, if you like Latin stuff, some people like to write QED. That's Latin. That's an abbreviation for the Latin quod erat demonstrandum, which means it has been shown. Or you can just put like a square. That's more less Latin-y. Okay, I like to use a square, but that's a valid proof. Okay. Okay, we're out of time. We're going to continue tomorrow. Thank you. Okay, let's start. Good morning. Couple of things. So one thing I want to do is I want to make a small correction. Yesterday I defined these symbols, and these we're going to use. What is perhaps not quite accurate is to say that these sets are subsets of the reals, and in particular that means that by definition they cannot be intervals. The point here, of course, is that if I write something like this, for instance, I want to think of this minus infinity to infinity as something like a closed interval, so the endpoint's included. So somehow I would like to imagine infinity, for instance, positive infinity, as an element in this set. Okay? So that is the difference between this, for instance, and the reals, where I would use open braces, because infinity is not a real number. It's an extended real number, is what we're going to say. This is not too important, really. Ultimately, we would like to be able to make sense of things like, oh, the limit of this thing goes to infinity. Because, for instance, we would like to be able to say, oh, you know, there's a distinction between, there's a difference between limit of, let's say, x squared as x goes to infinity, being infinity, and let's say limit of sine of x, let's say as x goes to infinity, being undefined. In calculus, probably you've called both of these divergent, but this is somewhat different than this. So this keeps oscillating, which doesn't sort of stabilize anywhere. On the other hand, this does stabilize. It keeps going to infinity. So these are somewhat different behaviors. And we would like to be able to make sense of this somehow. And for now, we can just imagine this infinity and minus infinity to be a symbol that essentially represents this. Next week, when we start talking a little bit more about reals, I'll say more about how to perhaps make more accurate sense about these symbols, positive and minus infinity. And just to reiterate, we had these Lego pieces notation that we were using. This is this French notation. So this is this extended reals. I think this is the notation they use in the textbook, R with a bar, okay? And so this is minus infinity to infinity, endpoints included. So you allow positive infinity or negative infinity. Also, and if I wanted to use unions and stuff like that, I could say, oh, I have the set of real numbers here, reals, and I wrote it here too. You take any real number, all real numbers, you adjoin to this another point called infinity, and yet another point called minus infinity. And you get this extended reals. Okay. And how do I visualize this? This is the real line, and I'm imagining that there is sort of yet another point here that is labeled infinity that kind of goes, so if you sort of like go this way, you reach this, and in the other direction, if you keep going, eventually, somehow, you reach minus infinity. Again, let's not worry too much about what these mean. These are obviously, at least philosophically, questionable statements. Let's just take it for granted for now. Hopefully in time, it'll make slightly more sense. Okay. Now, what I really want to spend time on today, oh, I should say one more thing. So right after this class, I'm teaching another class in some other building. So I typically need to leave fairly fast. So if you have questions, probably if you try to ask them, I'm going to try to sort of just get out of the question very fast. So if you don't want me to be a politician, it's better to sort of ask it maybe before class or send an email or something like that. Okay? This is not anything personal. Okay, so there's that. Third thing, I think we have some hope for a different room. So yesterday I was able to, so Professor Zhu suggested a couple of rooms that are available. I checked them, and one of them seems to be much more applicable for our class. It's a standardized room in JTB, I think. If that indeed happens and they're able to make that connection, make that change, you'll see it in the schedule, but I will send an email as well. And whenever I send an email, I'm going to use the Canvas. Okay? If you go on Canvas, there's an inbox there and stuff like that. I'm always, 99% of the time, I'm going to use that. Okay. What is more important for us is, well, these three different ways of using or building new sets out of older ones. And in fact, the third one is the most important. First one is what is called the Cartesian product. Okay. I'll define what this means in a second. Second one is what is called powerset. Third one is the set of functions. Now, this is the most important thing, because analysis, calculus, is all about functions. And part of why we've been sort of talking about all this stuff is we would like to be able to define what it means for something to be a function. Okay? So we'll get there in a second. Let me first define what a Cartesian product is. If you have two sets, x and y, you get to take their product, and that's the Cartesian product in a sense. And what does this mean? It means this. let x and y be two sets. No, two sets. Okay. Then their Cartesian product is a new set, okay? And this I'm going to denote by x times y. Okay? I'm saying this is a new set that I'm building out of x and y. And this is going to be, again, I'm going to use the set builder notation. You see, I've been using this so much, so often. So open braces, bar, close braces. And what was the formula? Here you put the general form of the elements that you want in your set. And here you put the conditions, right? And so I'm saying this set is a set of things of this form. These are what are called ordered pairs or ordered tuples. That's just the general form. And on the right-hand side, I'm going to need to write down the conditions. And of course, what I want to say is x comes from x, y comes from y. Okay. Of course, perhaps the best example of this is something like the plane. R2, basically, you're just, when you're writing r to the 2 to represent the plane, you're saying r multiplied with itself in this sense. Okay. Okay. Of course, Rn, this done many times, and so on. Any comments or questions about this? I know that this week has been sort of these more abstract stuff. Starting from next week, we're going to really specialize on the types of objects we're looking into. That's the first method, Cartesian product. If you have x and y, that gives you x times y. Power set is yet another way of constructing new sets. It says if you have an x, from this you get some other set denoted by curly p of x. And this is what is called the power set. Let me now define it. Let x be a set. Maybe I should have said, then their Cartesian product is the set which is this. Let x be a set, then its power set is p of x. I want to define what this set is. Again, I'm going to use the set builder notation. And here, something bizarre is going to happen. The power set of x is the set of all subsets of x. Okay? In other words, it's the set of all those a's such that a is a subset in x. So in a sense, this kind of allows you to relate subset of relation, in other words, this symbol, and element symbol. Because you have this idea, okay? A is a subset of x is equivalent to saying that A is an element of the power set of x. How many of you have seen something like this before? Maybe with a different name? Okay. So let's look at an example as usual. Again, don't worry too much about these matters. Very rarely we're going to use something like this. And even this, we're not going to use this much because this class is mostly about single variable. Once you switch over to 3220, multivariable calculus and stuff, this ends up being important, of course. But so for instance, let's look at this. X, let's say, is a set that contains two things, A and B. Okay? This is a set that has two elements. What is power set of X? It's again a set. And of course, I can write this. But the point here is I want to write it out as a list of things. Open braces. Now, I didn't mention this, but this is a technicality. There is something called the empty set. It's the set that contains nothing. Okay, so you have to include that as a subset. So nothing is included in anything, for instance. Just like, in terms of numbers, 0 is kind of iffy if you start thinking about it. There's a similar thing for sets, and that's the empty set. So empty set. And you might also see this symbol. You would open braces, don't put anything in between, close braces. So you say, oh, this is a valid set. Okay, open brace, close brace, there's nothing in it. Okay, this is kind of a technical matter. But what else do we have? Well, we have the subset that contains only A. Okay, so comma. The subset that contains only A, you see, this is a subset of X, which means that it has to be an element of P of X. And there's another one, set that contains only B, and then finally X itself. Any comments or questions about this? Okay. The third item is the most important thing for us, and it's going to take a while. We're going to start with two sets. And we're going to have a new set that I'm going to denote by f of x semicolon y. And so if I have two sets x and y, I want to talk about a function from x to y. And this is going to be the set of all functions from x to y. But before even defining a function, we need to define something slightly more general. And that's called a relation. Okay? How many of you have heard of this word, relation? Okay. What if I say something like horizontal or vertical line test? Okay. So relations are sort of more general things than functions. And you have these tests that you use to figure out if a relation is a function. Okay, so we're going to first define a relation. Let x and y be two sets. then a relation from x to y so the direction is important here, is a subset of x times y. Okay. Now, you might say at this point, well, if a relation is nothing but a subset of x times y, why not just call it that? Well, the point is, this is sort of like an abbreviation. What we're going to do in this class is that we started with sort of simple things, simple objects, and we're going to start defining new things in terms of simpler things. But they're going to have multiple parts. But just to abbreviate, we're going to sort of package certain ideas, and we're going to say, instead of saying, oh, this is a subset of x times y, I'm just going to call it a relation. Okay? So as we keep advancing, we're going to keep compacting the stuff that we discussed before. So everything is going to turn into sort of like a technology, like a machinery, right? Okay. So let's try to write this in symbols. So for instance, I would write something like this. R would be a relation. I'm saying this is a subset of x times y. Or of course, if I wanted to use this powerset notation, I can ultimately sort of match and use a bunch of these different constructions. I could also write R is an element of the powerset of x times y. These are all the same things. Okay. By the way, once we start talking about integral calculus, we're going to start looking into p applied to itself. So we're going to look at p of x. Okay, we'll get there later. So I want to give a couple examples, okay, because this is somewhat hard to parse. And maybe even before giving examples, I should give you some sort of heuristic. Even though I haven't defined a function yet, a good way to think about a relation is, well, it's basically like a function, but maybe it fails the vertical line test, kind of a thing. Meaning, a relation is kind of like, well, it's a partially defined, multi-valued function, okay? So maybe it fails the vertical line test is what I'm thinking, but a relation pretty much is like a function for me. So idea, I'll write it here. I'll write it here. So heuristic relation is pretty much partially defined multi-valued function. And here is a piece of math lingo. Whenever you see something like this, okay, there is probably some implicit usage of the word possibly somewhere. Okay, so when I say partially defined, I really mean possibly partially defined. Maybe it is defined everywhere. We're going to talk about what that means later. And again, multi-valued, whenever I say multi-valued, I really mean possibly multi-valued. There's then sort of turns into rather bizarre things. So for instance, people would say nonlinear systems. But technically, linear systems are also nonlinear. Because when they say nonlinear systems, they really mean possibly nonlinear systems. Okay, so there are always hidden possibly, words possibly around. Okay. So what are examples? Whenever you're trying to understand things about these set theory stuff or logic stuff, the nice examples you want to think about are first finite sets, okay, and second intervals. First, you try to understand those because these we can in fact draw and all that stuff as well. So let's think about this. Let's say I'm going to take both x and y to be the interval from 0 to 1, endpoints included. Okay? So what is the intuition, of course? X is a segment like this, and so is y. The useful caricature for x times y often is to think of x as the horizontal variable and y as the vertical variable. Even though this class is all about like rigor and stuff like that, one of the methods that's going to work quite a bit is that you're going to see bizarre things. If you say, well, I don't understand any of this, I'm going to pretend everything is single variable calculus. And that intuition, if you interpret it correctly, is going to work actually. Okay? So I want to think of this x times y as a rectangle, or in fact, as a square. Does this make sense? And perhaps just to be a little bit more clear, how did I build this out of this? Let me write it like so. I took the interval, it was the same set ultimately, but I took this and used it here. And the other one, I took and used it as the vertical. Okay. Any questions about this identification, this imagination? There's something non-rigorous happening, of course. When I say this set, I can imagine like this. Remember, I think on Monday or Tuesday too, I told you, well, we have this real line, it's a set, it contains rationals, and I don't want to define it, and it's basically like a line. And I told you there too, there is something I'm using there. Just because ultimately, from a formal point of view, sets are amorphous collections of sets. They don't have any shape. But that intuition that comes from single variable calculus, we're going to use throughout this class, and that's the only intuition that we're going to use ultimately. And so even though that is not super accurate to say, oh, the real line as a set is that thing, it's that line, it's going to work for us, and it's going to do us no harm. And just like that, here too, I'm using the same sort of intuition. So sets technically don't look like anything. Okay? But we'll get to pretend that it is. It's more sort of, gets more formal as far as I'm concerned. Okay. Of course, what is the idea? Well, the point is, any point in x times y is supposed to be a pair of numbers, x and y. If that is the case, well, certainly, any point on this rectangle is represented by one x coordinate and one y coordinate. Okay? Just to reiterate, I would write it like this, right? So you can write it like so if you want. So that's our set. Any questions so far? Yes?
Is the R a set?
Yes.
It's not a real line.
This R,
Yeah.
you see that's why I introduced this other notation. When I mean the real line, I'm never going to use this letter. It's going to be an R, but with a dash. Okay? Not the reals. Reals is special for us. This is some abstract stuff. When it's this specific set of real numbers, this is always R with a dash through. Okay? This notation is reserved for the real numbers. Okay, that's a good point. So technically, for instance, x times y is a subset of itself, which means that x times y is a relation from x to y. So x times y is a subset of itself, and so x times y is a relation from x to y. What does this mean? This means from the perspective of x times y, if I imagine it as a relation, it says any x is related to any y. This is kind of course, nothing in a sense. You see, one of the issues with abstract math is the moment you try to be more rigorous and precise, there are a bunch of like edge cases and things that are technically valid to say, but that doesn't mean much really. That's going to happen. Here's another example. Same x and y. This time, let me define R to be the set of all xy's such that, well, x equals y. This is a subset of x times y, so this is a relation. Okay? Okay, and what is a relation? Or how could I imagine this? Well, this is, of course, nothing but the diagonal. Okay? Right? And what does this say? The only y that is related to x is x itself. That's the relation. Here's another example. Again, x and y, let's say, are both 0, 1. Now I'm defining R to be xy such that x is less than or equal to y. And this is again a subset of x times y, so it's a relation. It's almost like all of these symbols that we've been using are indeed ultimately relations. And remember how I mentioned this set theory assumption that everything in math is ultimately a set? Well, really, the way you make sense of this is you imagine it to be a set, imagine it to be a relation. But then a relation is nothing but a set in some subsets, okay? Nevertheless, this is again a relation. And how would I imagine this? Well, I would have to include the diagonal, but I would have to include everything underneath also. Okay? That's a relation. Okay? A couple more examples. Maybe one more. I don't technically need to take x and y to be the same. I kind of like it because then I can just draw a square. But maybe we can do this. Let's say both x and y are the reals. Okay, and let's define the relation R. And by the way, just because we're talking about relations, you don't need to necessarily use the letter R. If you want, you can use some other letter, of course. Let's say S, x and y, such that x in absolute value equals y in absolute value. How does this look? Can you give me a shape that would correspond to this? Meaning, here, for instance, it's the diagonal line. Here, it's a triangle like so. How could I imagine this set S? There is some wedge here, but perhaps you can describe it slightly more accurately. How would you even start answering this question, perhaps? Let's go back to that.
Are you asking for like a geometric representation? Just do normal xy axis and then it would be both diagonals, so positive and negative one.
Okay, so what your colleague is suggesting is that you don't really mean that the axes should be included, I guess.
No.
Okay. Yeah. So what your colleague is suggesting is that, oh, x times y, in this case, is the plane. I'm going to draw the x and y axes just to orient myself. Okay? And then your colleague is suggesting, in this case, you should be seeing an x figure. Okay? That's a claim. Any comments or questions about this?
Isn't it because they're both the absolute value, there should be nothing in the negative, so it should be a V, right?
Okay, that's a good question. Maybe you can answer this question. Can you try to convince them?
Yeah, well, negative x and negative y are still contained in it. It's just the condition is that the absolute value of those are equal, so you still have the negative axes as part of math.
Well, you could do that, okay? Of course, what you're saying is correct. But perhaps it would be more convincing if you could give an example.
Oh, yeah, but -2 would still, for -2 still works. They're both part of the reals. And the absolute value of -2 equals the absolute value of -2. But you would see it in that quadrant 3.
Does this make sense?
Yeah.
What your colleague is suggesting is, well, -2, certainly it's a point in R times R. Okay. We're testing out this point. Of course, in this representation, it would correspond to this point. Well, you're asking, is this specific point included in S? Well, you look at the condition. -2 in absolute value is 2, and so is this. So it has to be included, you see. Does this make sense? And of course, -2 comma +2, which would correspond to this point, again, it satisfies the condition that defines a set. Okay? Okay? Yeah?
So, in other words, did you say like the relation line is the acceptable inputs rather than the outputs?
Say that again?
Like our relation line for this most recent example, you could say that.
What do you mean by the relation line?
Or the relation.
Set.
Yeah, the set, or just kind of like the geometric shape we drew. Does that represent all the available inputs?
What do you mean by input?
Because we're saying that we can input negative numbers, and our graph shows that we can input negative numbers, but our outputs would all be positive, which would make that B graph.
Well, in a sense, okay, your colleague is taking the other class I'm teaching, and there I started using input and output as words. Perhaps, but that's a sort of 2000 level class. The part of it is that I don't want to go into that because it's kind of dubious what is an input and output. Okay, I'd rather not use words like that. What's an independent variable and what's a dependent variable? Okay, that kind of I think eventually makes things complicated. And in fact, further on, we're going to study what is called inverse function theorem. And that actually is going to start, so through that, we're going to start confusing what is an independent and dependent variable, in fact. Right? I know I didn't technically answer your question, but maybe we can discuss that later. I want to give one more example, okay? And then that's going to be the final example. Yes?
So is that relation that we just proposed right there?
Yes.
Is that a relation? Is that set a subset of x times y?
Yes. Yes. Yes.
Oh yeah.
Yes. Yeah, I realize like I'm not doing anything. Like I'm just like coming up with new words to describe things that are straightforward, but eventually these are going to sort of build up to more complicated things. I'm just trying to get you accustomed to, at the very least, the set builder notation. That we're going to keep using. One final example I want to give, I think, and then we're going to define something else. Again, let me take x and y to be R. Let's say C is the collection of all x, y, such that x squared plus y squared equals 1. How do I get to imagine this then? It's a circle, okay. Circle, to be more specific, centered at the origin of radius 1. Okay, that's a relation also. So basically, what does that mean then? A relation pretty much is a shape. Okay, this we're not going to go this far. Once I define a function, we're pretty much never talk. I mean, we might sort of use it a little bit, but the main thing for us are going to be functions. But for instance, when it comes to image processing or being able to sort of computer vision, imagine sort of like the shape of a letter. like number 1 or the letter A and stuff like that. These are not technically functions, but they are relations. So it ends up being very important to be able to think about shapes in a square like this as a mathematical object. This is not the only way of doing this, of course, but this is one of the ways. Okay. So these are, yes?
Sorry to go back to this.
Yeah.
I'm just confused at the hesitancy to use input and output, but isn't the whole point of a relation to map one set to another set?
Yes, but so what is the input here?
Little x and little y,
And what is the output?
the little x, little y pair.
Oh, you can think of it that way, of course. I guess your colleague is suggesting somehow, how do you even write that? X and y, and then you take it, turn it into xy pair. So I guess you're talking about something like this, something that takes 2 inputs.
Right.
Yeah, you can talk about this, of course. But this, in a sense, it gets more formal, perhaps. Eventually, you do use things like this, but I guess if that's what you meant, was this also what you meant?
Something like, yeah.
This is perfectly valid, yes. Yes. Yes.
So a relation is a set, which is a subset of the Cartesian product of x times y.
Yes.
Right? Can you give a counter example that is not a relation?
Good point. Well, I could, but I think that would take the topics rather too far. Because the point is this, okay? I'm just like bypassing a bunch of like logical stuff. But there are certain things like non-well-defined statements. Okay? So if I were to say, so I could look at something like this, for instance. Okay, let's give an example. A non-relation. Okay. X and y are both equal to r. Let's say n. Let's say xy such that x equals y. If you set up a quantum experiment and there is some random thing happening, and it says quantum experiment says yes. Okay, you have a quantum computer somewhere. Okay, and it's an algorithm. It prints out a Boolean variable. Either it says yes or no. And x not equal to y, else. Just because I can write things down, and I can even make sense of this we're not going to take as a relation. Okay? Even if you know what a quantum experiment is and blah, 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 the point here is that there's something random happening. And in this class, we're not going to talk about anything random. So this is not a well-defined relation for us. Another thing I could have done is same thing, x equals y. If I go out on the street, find someone, ask them, should I put it in? And then you put it in the definition there. Technically, you can write it like this, of course. There's nothing stopping you, but that wouldn't be a well-defined relation. Okay.
Just because it's not the subset of the Cartesian product.
Yes, but the point is, what you get to use on this right-hand side as a condition is rather limited. Okay, you don't get to sort of do very crazy stuff. Okay. That's why I didn't want to mention this. But you're right. The point here, I guess your colleague is suggesting, is that, okay, all of these are relations, but if a definition is supposed to be valid, there should be things that are not relations. I get your point. With all of the, when it comes to these foundational stuff, you can do these kind of things as well, but that takes us farther and farther from calculus. So the way I'm teaching this class is rather biased toward calculus. Of course, we're going to be rigorous and stuff like that, but ultimately, if something eventually is not going to be related to the fundamental theorem of calculus, some proof of it, I don't really care that much about it. Does that kind of make sense? Yeah. I mean, there are areas of math where they really talk about or think about what these things actually mean if this is valid and stuff like that. Okay? The other day, one of your colleagues mentioned something. It's like you look at the set of all sets and stuff like that, and you sort of set up a self-referential statement, and somehow logic starts breaking down. Okay? We're not going to need this. You can break all this stuff down if you force it. Okay? And in full transparency, I'm also not very knowledgeable about these foundational matters that much. All I know from a pragmatic point of view is that if you force it too much, it's going to start breaking. Okay. Okay, I think we're out of time. We're going to continue on Friday. Thank you. Yeah. Okay, let's start. Good morning. So the first problem set is up on Canvas. I'm not going to distribute the physical copies, but if you go right now on Canvas, and if you look at the assignments tab, under the first assignment, the problem set 1, you're going to see a PDF file. Okay. I'm going to say a couple more words about all these things, the problem sets and so on Monday, I think. For now, I'll let you read through the problem set, and I would also suggest to you that you should probably start. We'll talk about the logistics later. One thing I want to say is that especially with this course, it's going to be very important to sleep on some of the ideas. Many of the problems that are in the problem set I've designed so that at least some of them you won't be able to solve in first try. Okay? So you're going to need to sort of sleep on it and stuff like that and go back to it and so on. And I would suggest that you start each problem set the day it is submitted on Canvas, so the way I release it. And by start, I mean maybe have a look at the problems, see what they're about, maybe try to guess which ones are harder, which ones are easier, try to have a sense as to what will be the main sort of complication, and then keep working from there. Another thing I want to say also is that because this is an advanced math class, as you see, so for instance, there's a first section, it's background. I'm just saying a couple words about what this problem set is about. Then there's some stuff about AI, if you want to use it, or computer algebra systems for calculation purposes and so on. And then in section 3, you have the real problems, what to submit. I also have sort of some general prompts as to how you should be approaching statements here and stuff like that. One thing I want to say is that once you start looking into the problems themselves, you're going to realize all the problems are stated as neutral. Okay? So these are typically not leading questions. I'm just going to say something, and it's going to be your job to even figure out if what I'm saying is correct. So that is to say, you see a claim. First things first is to figure out, is this actually correct? If it's not correct, then that means that you need to come up with a counterexample and so on. Now in lower level classes, typically in each problem you would see something like justify your work, prove this, claim this, whatever, all these type of things. In this class, it's going to be the other way around. If there's a problem where I'm not expecting you to prove anything, and there are certain parts like this, that's going to be explicit. If I don't state anything, that means that I'm expecting a proof. Okay? I'll let you have a look at this problem set on your own, and Monday I'm going to spend more time maybe answering your questions as well. I think for now it suffices this much information about the design. Are there any other questions about perhaps the syllabus or something else? Okay. Now, for those of you who are interested in sort of like more foundational aspects, this is not really our concern in this class. I'm just giving you the bare minimum so that we can go ahead and do things. The classical stuff for this is written by someone called Enderton. One of them is Mathematical Introduction to Logic. The other one is Elements of Set Theory. Now remember, last time we were talking about a bunch of relations and stuff like that. And one of your colleagues asked, what is an example of something that is not a relation? I kind of gave an answer, but I was really grasping. And so this really points to something. Whether or not something is a relation is not going to be that much of a problem for us. For us, that's sort of like a philosophical problem. Is this a relation or not? Okay? Because ultimately, whether or not something is a relation is asking whether or not something is a set. And I was vague about what is a set to begin with. So, the question of what is a relation and what isn't, this we're going to think of as a philosophical question. Okay, when I write this, that means that I'm just designating this as something I'm not really interested in. There are other math classes, like, again, I'm mentioning this to you, where these kind of questions are important. Not for this course. What is more important, though, is the issue of a function. So we're going to define functions in terms of relations, and then it's going to be a problem whether or not a given thing is a function or merely a relation. Okay? And alternatively, you're also going to see this phrase, this function is well-defined, or this function is not well-defined. That's going to sort of show up naturally in calculus. Okay, so I'm just going to leave it like this for now. My aim today is to really switch over to functions. Remember, we had 3 different ways of constructing new sets out of old ones. One was the Cartesian product. The other one was powerset. Third one was, I told you, it's a set of functions from x to y. So we need to first define what a function is. And really, calculus is all about functions. Is there anything else I want to say for now? No, I think we can keep going. So here's a definition, okay? It's going to sound a little bit roundabout, but ultimately, we're going to end up with an object that we're going to call a function that does match with any other context in which you use the function in calculus, for instance, in math in general. And so it goes like this. Let x and y be 2 sets, and R be a relation from x to y. What was the definition of a relation? This is nothing but saying that R is a subset of x times y. Now you're going to see something like this as well. Technically, this is redundant. First I'm saying R is a subset of x times y, and then I'm explicitly saying let this be a relation too. Okay? Don't get confused about this. This is something that people do quite often. And remember that we were thinking of relations intuitively as shapes. Well, if that is the case, for functions too, if we want to visualize them, we think about their graphs. So we're going to, in fact, first look at graphs and then deduce functionality from that. And so I'm going to say that R is the graph of a function. Okay, that's the definition. If it satisfies this property. Any point in R is a pair of points in x and y. So x1, y1, this pair is a possible element of R. So I'm taking two of these, and I'm saying if the x coordinates are the same, then the y coordinates have to be the same as well. This is essentially abstracting out the so-called vertical line test. Right? I'm saying if the horizontal components are the same, that means I'm looking at one vertical line, this line has to hit this shape R at exactly one point. Okay? So let me record that. This is an abstract vertical line test. Oh. Okay. Now we keep going. In this case, I'm going to define a certain set A. And in a second, I'm going to tell you what this means as well, the domain of a relation. But given any relation, we can define a certain set in the first coordinates. Again, remember, we're using the set builder notation. A, I'm defining to be the set, okay, of all those x's in X such that R relates X to some y in Y. Okay? That's just a set. Now I keep going. If I define the set A, then for any x in A, because of the fact that I'm assuming that R is something that satisfies this abstract vertical line test, there is a unique y in Y such that xy is in R. And remember, this was my notation for unique. There exists a unique. Without the bang, or without the exclam, this is just exists. Could be one, could be many. I'm saying when you put an exclam, now there's a unique one. There's a unique y in Y such that xy is in R. And because of this, this unique y in Y we define as f of x. We define f of x as, I should say. Okay. We further write f colon from A arrow y. Okay, now I'm introducing notation for functions. R equals graph of f, which is defined like so. And call f the function from A to Y whose graph is R. Okay. with all this said, now we want to switch over to yet another definition where function is the main item. But we're going to use essential this construction. So let's maybe start a new definition. Let x and y be two sets. A function from x to y is the function from x to y whose graph is some relation Okay. So what is the difference between the first definition and the second definition? Basically, the second definition says, or let's start with the first definition. The first definition is more explicit. It says, really, I first think about relations, and then in terms of relations, I define functions. The second definition says, well, any function ultimately comes from a relation, but I don't want to sort of mention it. I'm sort of suppressing that. It's not a major issue what this difference is, insofar as you understand this condition. And finally, I can define the set of all functions from x to y. Capital F of x semicolon y, these are capitals, is the set of all functions. From x to y. Okay. Any comment? Yeah, go ahead.
You have just two different y's. One, or is that one y is like a cursive y, and then a different y, or is that just arbitrary?
Which ones are you referring to?
Because so you have like on this for one this is for all x. There's an element of there exists a unique y that's an element of y.
Yes.
Okay.
So there's only, in this board, there's only a lowercase y. These are elements, and there's only one uppercase y. That's a set.
Okay.
Can you just read out what that bottom line on the left side of the board says?
This one?
Yeah.
This unique y in y, we define f of x as.
Thank you.
So the more intuitive way of defining a function would be from x to y, if you're looking into, would be to say for any x, you associate to x some y. So that's a rule, you would say. But rule is not a mathematical object, technically speaking. So you end up needing to sort of do this roundabout way. Maybe it's going to be better to think about examples. So for instance, let's look at this. So for instance, let's say x and y are both -1 to 1. Maybe I should put equality here. Let's say R is, well, this was something that we looked into, xy and x times y. such that x squared plus y squared equals 1. Okay, so this has the shape of a circle. Okay, and I'm asking, does this relation have the property of being the graph of a function? Okay, well, no, because, for instance, 0, 1 is in the relation, and so is 0, minus 1. Certainly, the x coordinates are equal, so the hypothesis is satisfied, but not the conclusion, you see. But 1 is not equal to minus 1. So R, this specific relation, fails to satisfy this property. Okay? Not the graph of a function. Question? No? Yeah?
Not yet.
Okay.
Thank you.
Does this make sense? Yeah, go ahead.
So a function is exclusively defined by its graph?
Yes. Yes. That's a very good point, actually, because in practice, as time goes by, we're going to be less and less pedantic about these kind of matters. And you'll just see in practice, even when you're doing abstract math, people would confuse f and its graph. For 99% of scenarios, that is benign. That's a benign thing to do. There's one issue I'm going to mention in a second, and that has to do with this symbol. Okay? F to the minus 1. How many of you have seen something like this before? Okay, so this is going to be an issue for us. There are two ways to interpret this. So because we're going to use the same symbol for two different, slightly different things. Ultimately, just because we're writing this is not going to mean that this f is an invertible function. Okay? Sometimes this is going to stand for the inverse of the function. Sometimes it's going to stand for what is called the pre-image. I'm going to mention that in a second. I'm doing, in a sense, all this so that we can explain what is happening here. We'll get there later. So that's an example of a relation that fails to satisfy to be the graph of a function. But let's think about something else. Or maybe even before that, let me mention why I'm calling this the vertical line test. Well, because of this, you visualize this like so. Right? So I have this. Oh, it's easier to draw nonlinear shapes first, then linear shapes. Okay. So the circle is R, and the square is x and y, or x times y rather. And so I'm fixing, right? I'm probing my relation by fixing the x coordinates. And that means that I'm looking at one of these lines, for instance. And I see, oh, if I use this line, the line hits the relation at 2 points. If, when you draw a vertical line, your intersection number is more than 1, that means that that relation fails to be the graph of a function. That's why this is called the vertical line test. Now, the point is, of course, you're allowed to use any vertical line whatsoever. So for instance, if I were to use this specific vertical line, it hits R at exactly 1 point. There it's okay, but there's a for all here, meaning for all vertical lines, the intersection number has to be 1. Okay? Does this make sense? So here's an example of a relation that satisfies the property of being the graph of a function. Again, the same x and y. Now I'm going to define, let's say, S to be xy in here such that x in absolute value equals y in absolute value. Okay. So now if you try the same thing, this time you're going to realize this guy satisfies the property of being the graph of a function. Okay. Except it doesn't. And I lied, because when you think about how this looks, this was a cross, right? So the shape of this is like so. This was an example we talked about last time. I probably use a different letter, but the letter itself doesn't really matter, right? It's what I'm deciding to call. See, so if I were to look at this line, for instance, do we see this? So, not. Let me just say not. By the way, throughout this course, every once in a while, I'm going to try to trick you like this. This is so that you get some experience with not necessarily believing in someone who has authority. Okay? It's good to, listen to people who know what they're talking about, but at the same time, some amount of doubt is an important matter. Yes, please.
Your red mark not is to answer what question?
Whether or not this relation satisfies the property of being the graph of a function. Very good. So, not a function. Not a function again. And finally, oh, go ahead.
Are x1 and x2 just any x's on the graph, or what are they?
What do you mean graph?
Like, for example, the absolute value of x equals absolute value of y graph that we did?
Well, I guess what I'm suggesting you to do is to not call this a graph.
Okay.
Okay? Graph is when you have the vertical line test. I want you to associate the word graph with the word function. Okay? Maybe you may want to call this like a shape or something.
Shape.
Yeah.
And we're using the abstract vertical line test on that, right?
Yes.
And so in that sense, like take that first, the lower point you drew, then what would x1 and x2 be at that point?
Okay, that's another good point. So when I write something like this, even though I'm using different symbols, so far I'm not saying anything about whether or not these are the same or not. Conversely, just because you have two things that seem different, they don't mean that it doesn't mean that they are different necessarily. They could be the same. Okay? So the thing itself is not the same thing as what you call it.
Okay.
Okay? This is like a subtle point, but it does make things sort of complicated at some point.
So we could call that lower point the x value could be x1 and x2?
Exactly.
Okay.
Yeah, so for instance, I would say something like, just to be a little bit more clear here, what does drawing this vertical line represent? Formally speaking, I'm saying, well, look at x1, y1 defined as 1 minus 1, and x2, y2 defined as 1, 1. formally, when I draw this, I mean this. Okay? And I say, oh, look, this is my counterexample to that statement. This allows me to witness that that doesn't hold for this specific guy. Okay?
Thank you.
Yeah, so these are sort of subtle things that we do, and it's just a game, you know, just like some shenanigans. But this is sort of the legalese part. Yeah, go ahead.
So I think last class you said that the which way the relation goes matter.
Yeah.
Like A to B.
Yes.
Is that because of how functions are defined, or are relations?
It's the other way around. It's because how relations are defined. But yeah, ultimately, you know how functions go, and somehow.
Oh, because functions are subset of all the relations.
Yes.
Okay.
Yes. I haven't quite looked into the literature of this, but the history of this, but obviously people were interested in equations like this. And they know that something like this defines, at least implicitly, y is a function of x. And so people know what a function should mean in a sense, but then they had equations like this as well, so they had to, they wanted to somehow make sense of this also in a formal manner. And then they realized, oh, if that is the case, then a function is sort of like a special case of whatever this is. As far as I understand, that is how things progress. Any other questions? Go ahead.
So the circle is a graph of relation, or
I would rather not use that phrase. I would say it's a relation. If you want to refer to this thing, this specific thing, technically this has no formal standing, okay? But if you want to call it something, I would suggest something like a shape. Okay? You can call this the shape of the relation R. Okay. Any other questions? By the way, shape 2 has a specific mathematical meaning, but we're not going to use that specific meaning in this class, so we might as well just use the word shape as sort of like an intuitive idea. There's something called shape theory, for instance. But anyway, it all depends on context in math. Okay, I wanted to give an example really now of a relation that is the graph of a function. These are examples of relations that are not graphs of functions. I'll keep this. I'll just draw it here. I'll just write it here. And so when I write this down, you're going to see, you're going to say, obviously this sort of is related to a function. So for instance, let's say Rs, let's say T. Again, the same set, x and y, such that, let's say, y equals x squared. If something looks like a function, at least for now, it is a function. Of course, what is the shape? Like so. And this satisfies the vertical line test. No matter which vertical line I use, I'm intersecting the graph, the shape, to be more specific, at exactly one point. There's something else called horizontal line test, but that is not relevant to whether or not a relation is associated to a function like this. Okay? If I were to use horizontal lines, that's also relevant, which in fact in the first problem set you're going to use, that's something else. That's about injectivity, you're going to see. Okay? Any comments or questions? Please.
so you would rather say shape as a relation, but graph, use that term in related to function.
Exactly, yes. So whenever you see the word graph in this class, I want you to think of the vertical line test. That that it applies. Okay? Any other comments or questions? Now, there are certain operations we can do with relations. Even though relations ultimately are sets, somehow it turns out to be the case that relations themselves, if you specialize to this specific type of sets, you have more properties. And I hope that kind of makes sense why that should be the case, because if you look at a specific sample of compared to your larger sample, probably you have more structures, right? You could say something like, okay, so for instance, something like this. If you were to say the favorite ice cream of every single human is chocolate, that would not be true. You don't have this. But maybe you can say the favorite ice cream of the human that is me is chocolate. No, it is correct. Okay, you have more structure now. Or you can sort of like build conditionals like this as well. Let me not get there. But the point being is that because relations are specific types of subsets, they have more structure. Okay? And because of this, they have certain operations, they admit certain operations that sets in general don't necessarily admit. We're going to talk about that later, I think, on Monday. Let me see how much time I have. Because I want to start talking about proof methods specifically. Yeah, I'd rather first talk about proof methods, and then maybe on Monday we'll talk about how to operate graphs, operate relations. So things like this, for instance. I want to sort of spend some time on what this means. So, proof methods. Now, there are basically 4 proof methods that we're going to use in this class. You don't need to know what these proofs are or proof methods are as sort of things in themselves, but you should be able to use them. Okay? Another thing that's going to be important, of course, is that hopefully you'll be able to parse when you're trying to read a proof what they're actually trying to do, what the proof is actually doing. So the 4 names of these proof methods that we're going to use are these. And these are, again, going to go back to just logic itself. But I want to first give you the general sense, and then at least start with maybe a statement from arithmetic and try to sort of give a proof of the same statement using different forms. First is what is called direct proof. Remember, we were talking about this Wason selection task. And one of the things was, you look at the 3 and you flip it. That's about this. Second, proof by contradiction. And this was something that I kind of mentioned when we were talking about whether or not this union set is an interval. Okay? And then the third is proof by contrapositive. And there's a 4th one. Proof by contrapositive. And this was, again, the other, the other act in the Wason selection task. We had the red card and we flipped that one, I think. Something like this. And then the 4th one is what is called proof by induction. Or maybe, let me be a little bit more specific. Let me call it mathematical induction. And to this, I also like adding what is called case analysis. Analysis. I think I'm going to postpone 4 to next week also, because 4, induction is somewhat of a different nature. It has a different nature. The first 3, they look very similar. Okay. So now, let me first briefly state what the forms of these are, at least for the first 3. So, say you want to prove something of this form. P implies Q. I know this kind of looks abstract and feels abstract, and I don't blame you if that is the case. In a second, I'm going to give an example. I just want to talk about the shape of the argument. Somehow, the claim contains a hypothesis and a conclusion. Direct proof, so to prove this directly, you assume P, do things, and deduce Q. Okay? Assume P, add magic, let me say, add math, deduce Q. Okay, obviously the middle part is the dubious part. And once we're done with logical statements and so on, this is going to be the main thing that we're going to spend time on. Part of why I'm spending this much time on logic and everything is that when you're trying to do problem sets and so on in this course, sometimes the issue is not going to be the math itself, it's going to be the logic. You're going to have issues sometimes parsing what is actually being said. I'm talking about all this stuff so that you have some tools at your disposal that you can use. And you're going to realize, oh, there's a different thing. So these two things are different. Somehow there's logic, and on top of that, there's math. Proof by contradiction goes like this. Again, you want P implies Q. And this is now how you prove. This time you say, assume P and not Q. You say, suppose the hypothesis holds, but the conclusion does not hold. Then you add some math and deduce something that is obviously wrong. So assume P and not Q, add math. Again, this is where math comes into play. Deduce false. Deduce false. Something false. You'll see examples of this, but when I mean deduce something false, I mean something like you assume, let's say, P and not Q, you do a bunch of things, and then ultimately you end up with 1 equals 0. You get something like this, that means you're done with this proof by contradiction. Proof by contrapositive, again, you start with something like P implies Q. This is what you want to prove. And this time, you assume not Q, do math, and then try to get not P. I'll talk about induction later. Okay? These are the general shapes of these 3 arguments. And surprisingly, you're going to realize somehow, for some statements P implies Q, one of these choices is easier. This is a bizarre thing, but it does happen. Sometimes it depends on your psychological makeup and so on. It's not super clear to me why certain people gravitate towards certain proof methods for certain statements, let's say. So, this is confusing. I want to fix a specific statement from arithmetic, not really the types of statements we're going to look into in this class, and prove the same statements using each of these three methods. Probably we're not going to have time to do all of them, but at least I would like to give you an idea. So the claim, let's say, is this. Let n be an integer, let's say positive integer, in fact. If n is odd, then 3n plus 7 is even. So claim. If n is odd, then 3n plus 7 is even. What is odd and even? Odd means it's an integer that is not divisible by 2. Even means it is divisible by 2. Okay. So, direct proof. And even before that, perhaps, let's try to parse this. What is P and what is Q? There are multiple ways of sort of parsing this statement in terms of logical things, but you can say something like so. These are all your hypotheses. That's P. This is Q. Okay? So P implies Q is the claim. Assume n is a positive integer, right? So this is the set of integers. And when I put a subscript greater than 0, that means these are the positive integers. N in this is just a faster way of writing the same thing. Assume n is odd. Then I need to open up. You see, now I need to start doing math somehow. By definition, I get to use the definitions. Odd means n is not divisible by 2. The only way an integer is not divisible by 2 is, well, it's 2 times some integer plus 1. There's no other integers. There's no other odd numbers. So I can say, thus, there is a k, let's say, that's an integer, such that n equals 2k plus 1. This technically is by the definition of a number being odd. Then 3n plus 1 plus 7 is 3 times 2k plus 1 plus 7, which then you rearrange and turn into this. And then you see that this is 2 times 3k plus 5. This is an integer because k is an integer. But then I'm saying 3n plus 7 is 2 times some integer. That is what it means for a number to be even. And that's the end of the proof. Okay. This is an example of a direct proof. We're going to keep working on this on Monday. Thank you. Have a nice weekend. And I'll see you then. See you on Monday.